Hi, this is Joel with O'Neill Dunn. I'm the director of the Spatial Analysis Laboratory at the University of Vermont, and in this presentation, I'd like to attempt to answer the question, what are the remote sensing fundamentals? We're teaching remote sensing during an incredibly exciting time. Drones, such as the one I'm pictured with here, have democratized remote sensing, giving us all the capabilities to go out and map our landscapes. LiDAR and active sensing technologies have changed the way in which we can capture data about the Earth's surface. And automated feature extraction technologies have allowed us to process billions to trillions of pixels to accurately map land cover and other features in ways that we never thought possible. It's also a challenging time to be teaching remote sensing. We're doing so during the midst of a global pandemic. There are dozens of remote sensing software packages that have regular updates, and the way in which we obtain information has changed. It's no longer through just conferences or journal articles. We have to stay on top of the latest developments by monitoring social media. Remote sensing has always been a challenging topic to teach. In the early days of film, we'd have to cover the principles of chemistry. Physics and the electromagnetic spectrum have formed our foundations, and now we have to cover new properties of sensors such as LiDAR. We've always discussed human cognition and the elements of image interpretation, and then how we attempt to automate that through various classification algorithms. We have to get across the principles of different data structures. We teach our students how to use technology, how to work with different software packages, how to store and manage data, how to download data from different portals. In these days of drones, we're teaching them flight planning, along with the corresponding rules and regulations. On top of this, we need to teach them domain expertise, how to read the terrain, maybe the elements of forestry, or civil engineering, or marine biology. And in today's world, other topics, such as privacy and equity and justice, deserve an equal footing. It's not surprising that we find ourselves struggling to keep up with all this technology, that we wonder what we should be teaching our students, and I think it really comes down to, what are the remote sensing fundamentals? What do we need to provide to our students so that they can adapt and thrive in a challenging and changing world? Remote sensing has always been both an art and a science, and my concern that in today's world is we focus too much on the science side, specifically the data science side, and that we've run a risk in the last decade of creating a new batch of professionals that are very proficient in processing large amounts of data using fancy algorithms, but may lack the domain expertise and qualitative skills needed to solve the pressing problems of the future. I believe the best thing that we can do to prepare our students for tomorrow is to focus on remote sensing tradecraft, coupling education with experience, theory with application, and domain expertise with technological know-how. It's so compelling to want to focus our curriculum on the high-end technologies, such as the new generation of artificial intelligence and the amazing things that deep learning algorithms can do. The reality is that it's probably only a matter of time before these fancy AI algorithms tackle the very simple problems, such as mapping all the buildings in our planet. What happens when we need to tackle more complicated tasks, ones that require not just strong programming skills or expertise in a software package or an algorithm, but true domain expertise, true understanding of the data? In short, what happens when we need remote sensing tradecraft? I'd like to walk you through some of the recent projects that our team of faculty, staff, and students have carried out that illustrate the importance of remote sensing tradecraft. Accurate wetland maps are incredibly important for both ecological and regulatory reasons. Wetlands are some of the most challenging features on our landscape to map. The automated approaches that we employ require an understanding of spatial filters, data fusion in which multispectral imagery, LiDAR, and climatic datasets are integrated into a single workflow. Topographic indices need to be calculated at the appropriate resolution, and we need to employ segmentation algorithms so that we can extract the features with both precision and accuracy. Our tree canopy assessments are a powerful tool for communities to help them understand how their tree canopy has changed over time so they can make improvements to their green infrastructure We're entirely reliant on publicly available imagery and LiDAR in order to carry out these assessments. Because these source datasets have been acquired by different vendors and processed to different specifications, determining true change from simple shifts or differences in the data is extraordinarily challenging. Accurate mapping of the change can't be accomplished just by developing an amazing training dataset and applying it to an AI algorithm. It requires extremely careful attention to detail, using morphological routines to maximize the strengths of the input datasets and minimize their weaknesses to represent change in a realistic fashion. When we employ drone technology to detect invasive species along utility corridors, we can apply our domain expertise to fly our drones with multispectral sensors just as those species are greening up, avoiding the need to purchase cumbersome and expensive hyperspectral sensors. When it comes to using drones to carry out critical infrastructure inspections, it requires a combination of the theoretical foundations of thermal imaging combined with hundreds of person-hours gaining experience to fly in these extraordinarily challenging environments. In the end, we need to keep in mind that what we're looking to do is to provide people with actionable information so that they can make better decisions. In this example, we're looking at the city of Boston, whose tree canopy has remained largely stable over the past 5 years. But when we dig into the data a little bit more, summarizing tree canopy change by neighborhood and breaking it down by land use, we see that in many neighborhoods, substantial tree canopy loss is occurring on residential lands, which is great cause for concern given the high proportion of residential land within the city of Boston. So what are the fundamentals? And perhaps more importantly, what should we be teaching? Well, we've got to emphasize the cognitive sciences, not just the elements of image interpretation, but more recent understanding of how we as humans identify features in remotely sensed data, such as scene gist. We have to give our students the opportunity, the ability to apply their knowledge and incorporate domain expertise. And we've got to do this in an environment that allows them to tinker, to make errors, and to learn from those. Theory will always be important, but we can't let it overtake our coursework. There are materials that we can get rid of, such as discussions of pixel-based classifiers, which are a far cry from the human cognitive approach that is used in object-based or AI algorithms. Finally, we can reduce the number of software packages our students work with. Buttonology is not what we want to teach them. The software will be constantly changing, and I think this is one of the exciting things about ArcGIS, that we have a single platform that we can train our students on from their introductory GIS class all the way through to their advanced remote sensing class.